So today I'm going to be talking a bit about what we do here at Unity, specifically a toolkit called ML Agents. And essentially, our goal at Unity is always one of our mottos is like democratize development. And one of the things we want to do is democratize machine learning. And this toolkit is one step in that direction. And I'll talk a little bit more about what that means and how you can use this toolkit in your own Unity projects. And then we'll conclude with a short demo of how to use the toolkit actually running and learning something. All right, so stay tuned for that. Okay, so let's get started. So games and machine learning have kind of been two sides of the same coin for a really long time. Here we have three popular games. The middle one's obviously a classic board game, and then two very popular video games, Dota 2 and StarCraft 2. And you can probably already think about like what the popular big AI advancements have happened around each of these three games. For instance, on the left, OpenAI 5, that was OpenAI's basically creation of a human-like bot for Dota 2. And on the other side, DeepMind has created AlphaGo and AlphaZero, both superhuman bots for Go and StarCraft 2. And all three of these had publicized events where these bots were playing against real human players, and they all did very well. And so we really see games as pushing the boundaries of AI research and advancing what we think of as intelligent programs, right? But we also see it the other way, where now, for instance, let's say in these three games, you wanted a really good bot to play against when you're not playing online. Wouldn't it be great if you could use this technology to build such a bot for you? And what we want to do is now we're starting to see, can we not code these bots? Can we not code these behaviors, but can we teach them? And this, you can get more intelligent behaviors, but also in many cases, you can save a lot of time. And I think as a developer, that's very, very interesting. So what do I mean by behaviors, right? So in games, there are many things that have behaviors and that you need to create behaviors for. For instance, you could have your player character. This could be the main character. It could be non-player characters that interact with your player character. That's kind of the most basic. And then you have squads of characters. These could be, one of them could be your player character, and then a bunch of them could be helping your player character. Or it could be a multiplayer game, and some of them are bots, but most of them are players. Finally, which is the little bit less obvious, is you could have the game itself be intelligent. For instance, the game world could be changing depending on the player. There could be a player assistant that's helping the player do certain things, or there could be game objects in the environment that need to behave a certain way, right? And today, basically, all of these are created through explicit code, and this works for most behaviors. You can use a behavior tree. You can write your state machines. In Unity, all of our game logic code is written in C#. That's why it says C# there. But it's all coded. And what we want to do with ML agents is start to move some of this code into the realm of machine learning. So can we use imitation learning or reinforcement learning to create these behaviors that normally would be written in code? All right, so, well, I keep talking about ML agents, so it's short for machine learning agents, but I think everybody must be wondering, what are agents, right? So if you're familiar with reinforcement learning, this definition is And at any given moment, this environment, so the environment could be like the game board or level or scene that you have in your game. This environment exists in a certain state. And the thing about the state is that the agent may or may not be able to see all of the state, right? So if you imagine like a board game like Go or chess, you would be able to see the whole board. But if you were thinking about StarCraft, where you have fog of war, or a first-person shooter where you only see what's in front of you, you don't necessarily see the entire state. So from this state, the agents take a subset of that, and these are called observations. And based on just these observations, not the entire state, the agent has to make decisions and take actions according to some policy. And this policy is the behavior of the agent. Now, in reinforcement learning, what we usually do is assign rewards to good behaviors and negative rewards to bad behaviors, so that during the learning process, the agent learns to maximize the reward using this policy. All right, so that's what an agent is in the context of ML agents. Now let's take a look at like what an agent would do in a game. So for instance, would be an example of like a shooting game, a first-person shooter. For instance, the observations, now again, the agent can't whole level, right? So it can't see where all the enemies are, but it could see enemies that are close to it. It could have maybe the view of the camera, and it could have its location, velocity, maybe how much ammo it has. And based on these observations, we give these observations to a policy. In our context, this policy is usually a deep neural network. And the neural network spits out actions. And the agent can take these actions, movement, shooting, ducking, and so forth. And throughout the game, this cycle repeats. And so like at every couple of frames, the agent will make a new decision, take a new action, and collect new observations. And that's our behavior. So that's an agent, and that's what an agent does in a game. How can we use these agents? Well, we kind of hinted at this a little bit. There's not just one way to use ML agents. For instance, the most obvious is, okay, let's, and we've seen this in AlphaZero and OpenAI 5. Let's use the machine learning agent to replace a player. So the agent is playing from the point of view of the player, and usually we'll have observations that reflect that. Maybe it's just the view of the camera. We could add more observations to help it. But it's playing as if it was a player. And this is very useful for testing games. Let's say you wanted to run your game 10,000 times and figure out any memory leaks or glitches or things like that in the game. You can use this bot to play through many, many times and report when there's an error, right? You could also use it to balance new levels. You could create a level, have the bot play it, and see what the win rates are and how difficult it is to finish the level. And this is useful when you're creating new content all of the time. You don't have to necessarily get playtesters to test all of these things. Finally, you can use these bots in terms of a multiplayer game. You could use these bots as stand-in for other players. Let's say you've created a bot that is more interesting and more intelligent than most players, most program bots. You could use this to face against other players. Again, the second use case would be non-player agents. So these are NPCs, companions, enemies, other characters in the game that are not your player, or game objects, or things in the game that are not your player. And because we can create interesting behaviors for these agents, the game becomes more dynamic and more interesting. Finally, the other one is not actual physical entities inside a game, but more the game itself. Can we have the game tune itself? Can we have it generate levels that are more interesting to the player? Can we tune the difficulty of the levels so to match the player's play style or behavior? You can do all of these with the ML Agents framework. So how do we actually go about creating agents and creating a policy for these agents? So to do these two things, this is the ML Agents Toolkit. It's an open source toolkit. After this talk, you can definitely go straight to this URL and download the toolkit and give it a go. And we provide a lot of the latest algorithms in deep reinforcement learning to help you do this. Finally, once you've done that, once you've trained an agent and you're happy with it, if you want to put it into a game, we provide a plugin called the Unity Inference engine. And this is essentially a neural network engine that runs accelerated on any platform that Unity supports, and which is a lot. So for instance, mobile, you can definitely deploy this on mobile, and it works fine. And if you have any accelerated capabilities like GPUs on the device, it'll use this. So let's talk a bit about these two components and how they would work in a game development pipeline. So here's the process. You first build a game or a scene or a simulation in Unity. You integrate ML agents into it. And that lets you train agents inside your environment. And finally, you can take those trained agents and embed them into your game. Or sorry, embed them into the build of your game and deploy it wherever you want. Okay, so let's talk about integration. So in ML agents, we provide three main classes that you can attach to different things in your game. And I'll show you what that looks like after the presentation in a live fashion. So we have the agent, we have the brain, and we have the academy. The agent is what we talked about before. That's the thing that makes the decisions, takes the actions, receives observations, receives rewards. And all agents that have used the same policy have attached to them the same brain. And the brain is kind of a stand-in for behavior, right? So that brain connects to the academy, which there's only one of inside each game. And the academy not only provides basically like a placeholder for the brain, but it also provides communication to the outside world, in this case, Python. So if you have a ton of machine learning code written in Python and you want to integrate it with a Unity game, you can use ML agents as just a Python API to do that. Or you can use our trainers to hook onto the Python API to do your training for you. So the Academy opens a socket interface and Python is able to connect to that. So there's different ways to set up a brain. If you have a bunch of agents using the same behavior, same policy, you can have one brain control however many agents you want. And these would all behave the same given the same observations, but they can be in different parts of the game or the environment or the level at any time. You could also have multiple brains, each one controlling a different type of agent. For instance, in this case, you have one brain controlling all the dogs, one brain controlling all the cats, one brain controlling all the rats, and you want each of these to have different observations, different actions, and different policies or behaviors, right? So you use multiple different types of brains to do that. So two ways to set up your brain. Okay, so you've set up your brain, you've put it into your game, you're happy with the integration. Now, how do you go about training? So we provide two ways to train your agents: reinforcement learning and imitation learning. Reinforcement learning, you give the agents a reward when they do something that you want them to do, and they learn through experience. They learn over time, over many trials and a bit of random search, what behaviors constitute maximum reward, and they try to maximize that. Obviously, this takes a lot of time, but you can speed up how fast your game is running pretty greatly because there's no human in the loop. And finally, usually these agents result in what we like to call superhuman abilities. If you define your rewards correctly, these agents will play the game in faster, better, more optimally than a human would. And this is desirable in some scenarios, but not desirable in other scenarios, right? Yeah, so let's take a look at an example of that. So what you're about to see is a game that a little game that we created. Essentially, there's this. If you've ever played Crossy Road, it's basically the same idea. Like you're this chicken and you want to cross the road without getting run over by a car. And as you can see, as the agent learns, it learns to avoid the cars and pick up all the presents. And the more time you give it training, the faster it's able to get through the level. So yeah, after you give it a lot of time, it's able to breeze through this level. And another interesting point about this game is that we're not actually giving the agent any insider information about where the presents are and where the cars are. The agent is just seeing what you see on the screen. So it's using the visual observation, is what we call it, to figure out what to do next. So that's our chicken demo. All right, so that's reinforcement learning. You probably saw in the last slide, like there's no way I could speed through that level that quickly unless I played for hours and hours on end. But let's say you wanted an agent that was more player-like and not necessarily superhuman. So then we provide imitation learning as well. In this case, you play the game through. You can do it offline or online. You can record the demonstrations, or you can play the game while the agent is learning. The agent learns to copy your behavior very quickly, but obviously you need to be playing the game. You can't just let it learn as you did in the first case. And the flip side of this is that the agent will copy your behavior exactly. So you're kind of limited to abilities or behaviors that are human-like or like you provided it. And this is good in some scenarios. Sometimes you want your agent to be very human-like, but if you want quote-unquote superhuman abilities, you wouldn't be able to do it in this approach. So here's an example of this. Let me pause this for a second. On the left, you have a human plate vehicle, and on the right, you have. Oops, sorry. I think I clicked on something that I shouldn't have clicked on. And on the right, you have the agent. And what you'll see in this video is that the agent on the right starts out crashing into walls. So we end the episode every time the agent crashes into a wall. And on the left, the human is steering, he's staying in the lane. And over time, the agent learns how to do that as well. So you can see after a couple of playthroughs, the agent isn't hitting the wall as much. And now it's doing a lot better. So you can see that the agent is also copying the nuances of the human behavior, like the twitches and the way it curves through corners and things. Okay, so that's the two ways you can train an agent. But there are many other things that we have in the toolkit. There's other algorithms that will help you do your reinforcement learning, like curiosity. We can give the agents memory. We can set up learning curriculums to help it learn faster. If you want to train quickly, you can actually spawn up many Unity environments at once, and I'll show you how to do that in a little bit. And finally, the Python API that I talked about before is compatible with external tools. Like if you wanted to bring in a learning framework from OpenAI or Google, you can do that and use your Unity games as the environment. And you can run it locally or in the cloud. And we're always adding new features. So definitely come and check it out. All right, so now we've covered training, we've covered integration. Now you want to go deploy that in a real game on a real device. How do you do that? Well, for that, so after you train your agent and you have a brain that you like, it's controlling the agents, it's doing the thing that you want. But what's under the hood? It's a neural network, right? And if it was a visual neural network, convolutional neural network, it could have hundreds of thousands to millions of parameters. And you need to do these large matrix operations across many, many agents in real time, right? And not only that, so depending on your network, you could have many, many different types of matrix operations. But not only that, it's running in a game. So it needs to respect the fact that you have graphics, you have physics, and you have other game logic. And all of these things need to meet some FPS number, right? You need to be able to maintain performance in your game. Likewise, you're unlikely to deploy your game just on Android or just on iOS. You probably want to do Android, iOS, PC, et cetera, et cetera, et cetera. And if you think about doing acceleration, like think about using NVIDIA CUDA or Apple's Core ML, you don't want to have to port your code to all of these different accelerator platforms, right? So to that end, we've created a plugin that we call the Unity Inference engine. And we build on a lot of the technologies that's under the hood in the Unity engine. The intermediate language to C++ compiler, a burst compiler, and compute shaders that are built into the Unity engine to do high performance computing, game logic. We're using that to do inference. And the nice thing about that is because the Unity engine was built to be platform agnostic, we can use the same neural network API across platforms. We can do CPU and GPU inference, again, across platforms, not relying on the fact whether you have CUDA installed or whether you're on an Apple device or an Android device. Exactly. And finally, it's fully integrated with the ML Agents toolkit. And you can use any of the trained models that you've created in ML Agents into this framework. Okay, cool. So we support all of these platforms, and it's not just game platforms. There's also, other things and VR, AR applications as well. And yeah, so now we have ML agents. We have the inference engine, and you can go deploy your neural networks inside Unity games, and it's all great. Let me show you a couple examples. So this is Puppo. This is kind of the unofficial mascot for our team. We created this dog, number one, to be cute, and number two, to show off what you can do without any scripting in terms of creating behaviors. So the dog's legs are physics-based. It's a ragdoll. And essentially, the agent in this case is controlling the force it applies on the limbs. And what we've done is be able to teach this dog to run. So you can see that the dog's running, but also we can also run many dogs at once because of the Unity inference engine, and the game doesn't slow down at all. And this is actually running on an iPad, and it's using Core ML to do the inferencing. So yes, this works on mobile devices, and the cuteness wasn't scripted. Yeah, so you can see the dog is running, and that entire behavior is controlled by the neural network. And so what does this mean for the developer? It means they don't have to code the running animation for the dog. And in fact, you get a more interesting behavior if you learn that behavior. Google Slides really doesn't make videos. Okay, so yeah, this dog. So throughout the presentation, you've seen these 3 slides. So this is Puppo, and that was the end result. But this isn't just a lab tool, right? Like, we're also looking at how do we integrate these into real games. And to that end, we've been working with a game studio, Jam City, to integrate ML agents into one of their games, Snoopy Pop. Shout out to them for working with us on this. And let me show you some of the results from that experiment. So Snoopy Pop is a bubble shooter. You're Snoopy down here. And so this game is available on the App Store right now. And you can shoot the bubble up to the board, and you want to match the colors. And if you match the colors, it clears. And your objective is to clear bubbles that have these birds in them and save them. So what we allowed the agents to do is look at the screen. So here's the observation that the agent's collecting. It's just an image of the screen. And choose an action, one of these directions to shoot the ball in. It can also swap the bubble with the next one if the color doesn't match anything. And we give it a reward based on the increase in score, the number of birds saved, a small negative reward for shooting, so to keep the episodes as short as possible, or to keep each level as short as possible, and a big reward for winning, and a big negative reward for losing. And so, this game is a bit more complex than the Puppo example. But the agent does learn a reasonable policy. So without training, the agent is just shooting randomly. After a bit of training, it's starting to clean out the board, but it's still not quite doing what we want. Finally, after a while of training, after a couple hours, it's able to win the game fairly readily. All right, so with the tools, internal tools, our latest experience, we've been able to train one agent to play many levels of this game. Obviously, it takes a lot longer than 2 hours, but we're working to get that time down. So yeah, this agent is a single agent, and it's playing through many levels of the game. And yeah. And I got stuck on many of these levels, but maybe I'm not the best Snoopy popper out there. So I think that's it. All right, so that's the final level, and it will win. Yeah, nice. So thanks. I'll go back to the slide. I'm going to show you guys a quick demo. Let me see if I can exit the... All right, so what does it look like to integrate ML agents into a Unity environment? Well, let me pull up Unity here. Oops, so this is the chat. Okay, so if you're familiar with Unity, this is obviously very familiar to you, but otherwise, here's the Unity editor. And in this editor, we can basically create our Unity environments. So this is a 3D environment here. You can zoom in, you can zoom out. And inside the environment, you have game objects. So here's a platform, here's a ball. And on the left here is the hierarchy of game objects. Each game object exists somewhere in the hierarchy. And this is all physics-based. So if I click run right now, the play button here, what would happen is all of the balls would drop and it would roll off the platform. And our objective is to train an agent that controls this platform to balance the ball. So what we're going to do is take a look here, and you can see that inside each of these platform objects, we've attached an agent script. And this agent script contains some C# code. And essentially, the main things that you want to look for are collect observations. We give it the position, the rotation of the platform, and the position of the ball. And finally, the action function, right? So at each time step, we give the agent some action, and it uses this action to rotate the platform. And so tilt the platform forward or sideways. And if the ball falls off the platform, we give it a big negative reward. And for every time step that it keeps the ball on the platform, we give it a small positive reward. All right, so this is a brain. Each agent is attached to a brain. And essentially in the brain, so this is a brain object, we can define, oops, that's not the brain, this is the brain. We can define the types of observations it has and the types of actions. We could add visual observations like the cameras if we wanted to. And this defines basically what is given to the Python side. So we have the academy as well. You need to instantiate one of these in each of your scenes. And you can put some logic in the academy, but in this case, we didn't need to. You could put, for instance, you may want to move all of your agents back to a nice location on reset, or you may want to do something to the environment on each time step. But in this case, we didn't have to. Finally, you notice that I clicked this control box. And what this control box lets you do is pass the observations that the brain is collecting onto the Python side for learning. So let's train that agent. So here we go. We have this script, ML agents learn. We pass it a config, we pass it the name of the run, and then we train. So it'll say, okay, click the play button. So I click the play button, oops. And you can see the agent right now is kind of randomly moving around. But if you give it a couple minutes, and by a couple, I mean like 1 or 2, you'll start to see that the mean reward here that's being reported by the command line tool will start to go up. And correspondingly, the agent will start to balance the ball a little better. Yeah, so you can already see the mean reward is going up a little bit. Yeah, I think this guy in the middle seems to be getting a little better. All right, cool. So that's one way you could train your agents. Let me see. Are you guys still seeing my screen? I think my computer does something weird. All right. So that's one way you can train your agents. You can also train your agents a little bit faster if you pass the environment directly. And if you wanted to go a little bit faster, you can go num AMVs and put more than one. So let's say put 3. So you can build your game and then run multiple of them at once on a screen. So you have see here that I have 3 of them running. And it'll train a bit faster. Or it'll train about 3 times as fast, depending on your environment. But you can see that because my computer is getting bogged down, each one of these 3 is running a bit slower. Let's see if it'll, yeah, so now you can see that even just after that couple of seconds, this one's being able to, balance the ball a little bit better. And we'll let this one train a bit. Yeah, so now you see that like over here on this third one, they're basically keeping the ball on the platform already. And if you give it like another minute, it'll not drop the ball at all. Okay, so I guess we're almost out of time, and I'd like to leave some time for questions. I noticed some on the chat already, and Bill, how would you like me to handle this?
Yeah, you can just go through the questions. I see, there are two, some type in the chat. There is also in the QA, another questions. You can, do either way.
Okay. So the QA is in the Zoom, right?
Yes.
Okay, let me go there.
There is a button next to the share. There is a Q&A.
Yeah. Okay. So I have opened that, and so we have a question from Mo, or Moe, I guess. When a model is being trained, how do you usually tell it to understand the rewards and the goal? Is it by telling it to look at something in the specific area in the screen, or by looking at internal variables under the hood? So basically, you give it the reward. So in the game logic, if you saw earlier, we called the function called add reward, and that essentially assigns a reward to the agent. And it's up to you what you want to use for this reward, but it does have to be internal to the game. Like the game has to be aware of this information. Okay, so I have another question here. Is it possible for the agents to outperform humans during learning? You mean during imitation learning, or during reinforcement learning? So with reinforcement learning, you can definitely outperform the agents. You can definitely outperform humans if you set your rewards correctly. With imitation learning, you're copying the humans, so strictly speaking, you cannot. Yes, it's possible to see the progress of a model. In the command line, you can see the model. You can also view the reward on TensorFlow board. Sorry, if you're familiar with TensorFlow, it's a nice web UI to watch the rewards increasing and the loss of your model and so forth under. Is there a way to leverage federated AI learning? What do you mean by this? Is this like a distributed training? So I guess if you mean distributed training, there's currently no way to do it in ML agents. You can do multiple instances on one large machine. For instance, if you go on GCP and make a huge, like a 32 core machine, you can run 32 instances of your game. But it is compatible with RLlib. So if you go to the framework called RLlib, Ray RLlib, this framework will support for distributed learning across many machines. And we've actually internally used this framework with the ML Agents Python API to do training across many machines. Okay, so is it possible to allow brains to inherit behaviors from other brains? So what you can do is train multiple brains. And so I showed one agent for one game object. You can actually create multiple agents and attach it, excuse me, to the same game object. And each of those agents could have different brains. And yes, you can have multiple behaviors for each of these brains, and they could control different aspects of the agent. TensorFlow. Okay, so how often training is the time-consuming part? So are there available pre-trained agents optimized for certain environment state observation conditions? So for each of those, so with our toolkit, we provide a bunch of example environments, and for each of those, we have a pre-trained brain. However, we don't have, and we're actually looking into doing something like this where we have pre-trained models for specific types. But the problem is that the type of observations each developer adds to their game is very game specific, and that changes your model. So you can't necessarily reuse those models. Yes, all of the sample projects, including the one that I showed you, is available on the GitHub repo. Yes, so reinforcement learning was used to program the walk of the dog. And what engine underlies the imitation learning? So both the imitation learning and the reinforcement learning is handled by TensorFlow. And yeah, TensorFlow is under the hood. If you install the GPU version of TensorFlow, it will accelerate it using the GPU.
There are some questions in the chat window. Do you want to quickly go through it to see? I think some of them probably already answered, but maybe some missed.
Yeah, let me take a look at the chat window. Okay, could you paste the GitHub URL? Yes, I can. So I guess most of these have been answered. What are the math fundamentals to master to be good at AI? Depending on the field of AI, for reinforcement learning, a lot of statistics. Resource burden running these instances really depends on the game. So the one I did was very lightweight. It's just the ball and platform. But if you're running something like Snoopy Pop or a full 3D game, you're gonna have difficulty running like 20 of them on your machine. It's gonna be really terrible. But I would say the minimum for a really simple environment is gonna be around 200 megabytes of RAM. And I will paste the GitHub URL. Actually, it's right here. So it's on the presentation. So it's github.com/unitytechnologies/mlagents. Let's see.
Can you copy paste to the chat window?
Yep.
Great.
Yeah, and on this page, you'll see all of these are the example environments that you can play around with and train agents in, and a bunch of different things. And check out the documentation for more details on how to use all of these features. It looks like we got more questions on the Q&A. What kind of TensorFlow neural network underlies the imitation learning? What is the reward cost function based on? So during reinforcement learning, the TensorFlow neural network it really depends on the input and the output, right? And basically the toolkit figures out, like, depending on the actions you have and the observations, what type of network to use. Actually, this is both true of imitation and reinforcement learning, although the structure is a little bit different. So if you have, for instance, visual observations, if you have cameras as the input, it'll choose to use a convolutional neural network with a fully connected layer at the end. If you have just vector observations, just float values, it'll use all fully connected all the way down. And the cost function is again different between imitation and reinforcement. For imitation, the cost function is how close does the action, so given the same input as the what the human is seeing, how close does the output match between those two? And it tries to match that. Okay, so the theory question, I have a question on integration. Is it possible to feed information through the model brain that is simply pixels on a screen? So the ML agents framework is specifically designed for a Unity environment. So you'd have to work around the pairing with the Python API, but I can imagine you could feed a video in there, for instance. However, we didn't design it for that purpose. Is there a URL to the PowerPoint slide? It's not currently shared. I can share it after the talk. What kind of neural networks are used for reinforcement learning and imitation learning? So I talked a little bit about that already. DNN for vector observations. If you're feeding images, you'll use a CNN. And you are correct, we actually do use RNNs if you enable the memory feature. And this enables your agent to learn a little bit about what it's seen in the past before it takes its actions.